So good afternoon, students. So we have learned about basics of molecular orbital theory, which is nothing but we have learned about atomic orbitals. We have learned about molecular orbitals. Then we have learned about how atomic orbitals are combining to give rise to molecular orbitals. Okay, how atomic orbitals are combining to give rise to molecular orbitals. Then after that we have learned about crystal field theory. Okay, how metal ion is forming bonds with the ligands, and how ligands are influencing d orbitals and splitting d orbitals into T2G and EG orbitals. Okay, as an example, we have learned octahedral complexes. We have learned about FeCN6 minus as an example of octahedral complex, and we have seen how ligands are influencing metal ion and splitting d orbitals into T2G and EG orbitals. Okay, in case of octahedral complexes, T2G orbitals are reducing in energy and EG orbitals are increasing in energy. Okay, why T2G orbitals are reducing in energy and EG orbitals are increasing in energy? Okay, it's a very important thing why T2G orbitals are reducing in energy and EG orbitals are increasing in energy. The reason why T2G orbitals are reducing in energy and EG orbitals are increasing, because EG orbitals are present directly on the axis of the ligands. Okay, so ligands are coming to the metal ion, and the EG orbitals are directly present on the axis of the ligand. Okay, that's why EG orbitals are increasing in energy and T2G orbitals are reducing in energy. After that, we have studied how electrons are getting distributed in octahedral complexes. Okay, that is just what we had learned in our previous classes. Okay, today we will see how crystal field splitting is happening in d orbitals in tetrahedral complexes. How crystal field splitting is occurring in d orbitals in tetrahedral complexes. Okay, let us see. So here in this slide we are able to see d orbitals. Okay, these are all nothing but d orbitals. Whatever is present on our left hand side is nothing but this is dz square. Okay, this is present along z axis, that is why this is dz square, and this is present along x and y axis. This is nothing but dx square minus y square orbital. Now on the right hand side, if you are seeing, this is nothing but dyz orbital. Okay, this is present in between y and z axis. Okay, this is z axis and this is y axis. Okay, in between y and z axis it is present. That's why this is called as dyz orbital. Okay, when we come to this one, this is nothing but dzx molecular orbital. Okay, because this is present in between z and x axis. This is x axis. Okay, coming towards us. This is whatever this perpendicular is nothing but the z axis. So this is nothing but zx dzx orbital. Now when we come here, this is nothing but dxy. Okay, this is x axis. This is we can see here. We'll just go back here. This is x axis and this is y axis. So x axis is coming towards us and y axis is like this, and this whatever is present in between is nothing but dxy orbital. Okay, dxy orbital. Okay, so this is these are nothing but d on the axis they are present. These are EG orbital. These are present in between the axis. That's why they are called as T2G orbitals. These are called as EG orbitals. E and T2. EG orbitals and T2G orbitals. Okay, and now in the diagram we can see here that green color dots are there here. This is one green color. This is another green color dot. This is another green color dot, and this is another green color dot. Okay, total four green color dots are there. Four green ligands. Okay, these are called ligands. Okay, they are coming towards the metal ion, central metal ion. So this is represented in the form of a cube, and in the center of the cube, at the culmination of all these axes, there is metal ion. Okay, so these ligands are approaching towards the metal ion. Ligands are approaching towards the metal ion. Okay, ligands are approaching towards the metal ion along the alternate corners of the cube. Okay, along the alternate corners. So this is one corner, this is another corner, next corner, ligand is not present. On the alternate corner, ligand is present. Okay, here down also, this is one corner. On the alternate corner, there is no ligand. And towards the next corner, there is one more ligand. Okay, so along the alternate corners, ligands are approaching the metal ion. So now, when they are approaching along the alternate corners of the cube to the metal ion present in the center of the cube, what is happening? They are neither getting influenced by the orbitals that are present on the axis, nor they are influenced by the orbitals that are present in between the axis. Okay. So it is now let us see how they are not influencing. Okay, we have to see that. In order to see that, we will just go to okay. This is here in this diagram. Okay, here in this diagram, we are able to see this is the d-jet square orbital. Okay, this is d-jet square orbital, and these are the ligands that are approaching along the alternate corners of the cube. So they are approaching along the alternate corners of the cube, and this is the d-jet square orbital that is present here in the cube, and the ligands are separated. They are distant apart to the d-jet square orbital. Similarly, to x square minus y square orbitals also, the ligands are distinct and they are separate. They are not in contact with the d orbitals that are present along the axis. Now, here is dyz orbital. Here is dyz orbital that is present in between y and z axis. Okay, this is dyz orbital. So this is around distant apart. Here we can see that this is the ligand, and here is the dyz orbital that is coming up here coming till here, and the distance is around a divided by 2. The distance is around a divided by 2. Okay, here the distance is a. Suppose let us say this distance is a. This is nothing but a divided by 2. The total distance from here to the middle of the cube is nothing but a divided by 2. So here also the ligands are not influencing the d-yz orbitals that is present in between the axis. Okay, here we can see this is alternate corners. The ligands are approaching. This is dz square orbital, not influenced. Okay, dz square orbital, it is not influenced by the ligands. Here we are able to see the tetrahedral nature of the tetrahedral complex in a cube, represented in a cube. This is very clear here. We are able to see it clearly here. Here also, this is another diagram which is representing the four ligands that are approaching the central metal ion along the alternate corners of the cube. These are the four ligands that are approaching the ligand along the alternate corners of the cube. So this is a cube, and this is a different color representation of the tetrahedral. Okay, this is a tetrahedral diagram inside a cube. Okay, this is another representation which shows the alternate ligands are approaching the metal ion, central metal ion along the alternate corners of the cube. So let us go back to our main slide. So this is our main slide. So here we are able to see that ligands are approaching along the alternate corners of the cube towards the central metal ion, and now the metal ion is present at the center, and the ligands are approaching along the alternate corners of the cube. And the thing is that the important thing we are able to see here is that the dz square and dx square minus orbitals are not influenced by the ligands, whereas dyz and dzx orbitals are also not much influenced, but they are influenced to a certain extent, because they are near to the ligands. They are near to the ligands. This EG orbitals are far from the ligands, whereas the T2G orbitals are a bit near to the ligands that are approaching. So here I have drawn this on board, and I have taken a picture of this, okay, of a tetrahedral complex. So we are able to see the cube here, and center metal ion is present, and ligands are present along the L minus is nothing but the ligands that are present along the alternate corners of the cube. And now this is nothing but x-axis, this is nothing but z-axis, which is here, z-axis above. To one side, this is x-axis. This is coming towards us is nothing but y-axis. Okay, here down is z-axis, which is going up, and this is x-axis, which is going to this side, and this is y-axis coming towards us and going back like this, y-axis. Now ligands are present along the alternate corners. We are able to see that this shaded region is z square, dz square orbital. Okay, is present like this, and we are able to see here that the dx square minus y square, this shaded region, dx square minus y square on x-axis, along x-axis, and along x-axis, and along y-axis it is present. Okay, so they are very far from the ligand. They are center, and they are very far from the ligands. We are able to see they are very far, whereas the in between, whatever orbitals are present in between centers of the edges, they are present along the centers of the edges. This is an edge of the cube, this is another edge, this is another edge, this is another edge. So these are all the edges of the cube. These orbitals are present along the center of the edges of the cube. Now when the orbitals are present along the center of the edges of the cube, they are influenced by the ligands. They are little bit influenced by the ligands. Okay, now when they are influenced by the ligands, what will happen, we will see in our next slide. Okay, so the dz square orbitals are not much influenced, whereas dxz, dyz, and dzx orbitals are influenced. When they are influenced, let us see what is going to happen. So here I have just made a note of all the important points in this slide. So tetrahedral complex, the metal ion is in the center of the cube, and the four alternate corners of the cube are occupied by four ligands. Okay, alternate corners are occupied by ligands. Directions of x, y, z axis point to the centers of the faces of the cube. We know that lobes of EG orbitals point along XYZ axis, that is towards the centers of the faces of the cube. EG orbitals point towards the centers of the faces of the cube, while the T2G orbitals point between X, Y, and Z axis, that is towards the centers of the edges of the cube. But the direction of approach of the four ligands does not coincide exactly with either the EG or T2G orbitals. Okay, the direction of approach of four ligands does not coincide exactly with either the EG or T2G orbitals. However, T2G orbitals are nearer to the direction of the ligands than EG orbitals, so the energy of T2G orbitals is raised maximum. Okay, so T2G orbitals are nearer to the direction of the ligands. So wherever ligands are coming, alternate corners of the cube, T2G ligands are present. So they are raised in energy, whereas EG orbitals are reduced in energy. In this slide, we can see that crystal field splitting of tetrahedral complex is smaller than crystal field splitting of octahedral complex. Okay, because in crystal field splitting of tetrahedral complex, why it is splitting is much lesser when compared to octahedral complex? It is a very important question. Okay, very important question. Why crystal field splitting of tetrahedral is smaller than crystal field splitting of octahedral complex? Because one main important reason is there are only four ligands. Okay, there are only four ligands, so ligand field is small. There are only four ligands in case of tetrahedral, so ligand field is small. Ligand field is small, whereas in case of octahedral complexes, there are six ligands, so ligand field is higher. The direction of orbitals does not coincide with that of ligands. Second point is, in case of octahedral complex, the direction of the ligands are directly pointed towards the d orbitals, whereas in tetrahedral complexes, the direction of orbitals does not coincide with the ligands. Thus, the tetrahedral splitting is always much smaller than the octahedral splitting. Okay, that's why tetrahedral splitting is always much smaller than the octahedral splitting. So here are d orbitals. Okay, these are all equal energy d orbitals. When ligands are approaching, they are increasing in energy. When ligands are forming a tetrahedral complex, Eg is reducing in energy, whereas T2G is increasing in energy. Okay, in between orbitals, dxy, dyz, and dzx are increasing in energy, whereas dx square minus y square and dz square are reducing in energy. Okay, so here d orbitals of free ion, this is nothing but average energy of the d orbitals in spherical crystal field. This is nothing but splitting of d orbitals in tetrahedral crystal field. Okay, so this is how splitting of d orbitals takes place in tetrahedral complexes. So here we can see comparison of crystal field splitting of octahedral and tetrahedral complexes. Okay, so this is the splitting of octahedral complex. We can see that it is very far apart. EG and T2G orbitals are very far apart, whereas tetrahedral splitting is much smaller. And tetrahedral splitting is reverse of octahedral splitting. Okay, here T2G will be down in octahedral, whereas in tetrahedral T2G will be up, where and EG will be down. In octahedral, EG is up and T2G is down. Okay, tetrahedral is reverse of octahedral, both in splitting energy and in the order which they are splitting. Okay, so here we are able to see that central metal ion, this is a cube, and center we have a metal ion that is present, and central metal ion in a cube we have central metal ion, and the ligands, these are the cream color ligands are nothing but the octahedral ligands, whereas the black ligands are nothing but the tetrahedral ligands. Okay, so in this diagram we are able to see both the octahedral complex and tetrahedral complex within one diagram itself, and here we are able to see the octahedral and tetrahedral splitting, crystal field splitting comparison. Okay. Now here we are seeing crystal field splitting in tetrahedral complexes. Okay, we are able to see here the crystal field splitting in tetrahedral complexes. It's very important. Okay, it's example COCl4 is an example of a crystal field splitting in tetrahedral complexes. COCl4 2 minus, and now CO cobalt in this complex is +2. Okay, it has +2 charge, and it has electronic configuration 3d7 electronic configuration. CO2 plus has 3d7 electronic configuration, and Cl minus of COCl4 2 minus is a weak field ligand. Okay, since Cl minus is a weak field ligand, it forms high spin complex. It surely forms high spin complex because Cl minus is a weak field ligand. So let us see the electrons that are getting distributed in d and s orbitals in cobalt element. So this is how the electrons are present. So this is D7 and 3D7, 4s2 and 4p0. Okay, 3D7, 7 electrons are present, whereas 4s, 2 electrons are present, 4p, 0 electrons are present. Now in CO2 plus, cobalt 2 plus, 2 electrons are removed from 4s. Okay, 2 electrons are removed from 4s, and 4 electrons are removed, 2 electrons are removed, CO2 plus, and rest all electrons are present. And in CO2 plus complex and in CO2 plus ion of COCl4 2 minus complex, what is happening is Cl minus is a weak field ligand, and here we are able to see that in case of spherical field, energy of d orbitals are increasing, and whereas in the place of tetrahedral field, they are splitting into Eg and T2G orbitals. Eg orbitals are down, whereas T2G orbitals on the upper side. Okay, so this is an example of tetrahedral complex. Now, important thing is that important point here is that since the complex has 3 unpaired electrons, so here in the complex we are able to see that there are 3 unpaired electrons are present. Okay, 3 unpaired electrons are present in the complex, and that's why this is paramagnetic in nature. So COCl4 2 minus is paramagnetic in nature because there are 3 unpaired electrons that are present. So that's why COCl4 2 minus is paramagnetic in nature. Okay, so we have studied about tetrahedral complexes. So how ligands are approaching in case of tetrahedral complexes along the alternate corners of the cube, and how ligands are not influencing EG orbitals much because EG orbitals are present along the axis, and they are influencing T2G orbitals that are present in between the axis along the centers of the edges of the cube. All right. Now, when they are present along the centers of the edges of the cube, they are influenced by the ligands, and they will experience repulsions, and that's why they increase in energy. Whereas EG orbitals, they occur along the axis and they reduce in energy. And another important point which we have noted is that the splitting energy of tetrahedral field is much lesser compared to octahedral field because of 2 reasons. Reason number 1 is nothing but the tetrahedral complex is reason number 1 is nothing but the tetrahedral complex is has only 4 ligands, whereas octahedral complex has 8 ligands, and tetrahedral complex 4 ligands are not along the axis. They are somewhere approaching along the corners. That's why the field splitting is much lesser. Okay. And in this slide, we have seen an example of a tetrahedral complex. That is nothing but COCl4 2 minus is the example of a tetrahedral complex. And COCl4 2 minus is an example of tetrahedral complex. And cobalt atomic number is 27. And here is the cobalt atomic number. And CO2 plus is nothing but 2 electrons are removed from cobalt, and CO2 plus electronic configuration is D7. and Cl minus is a weak field ligand, and hence we can see that this is a high spin complex. Okay, d orbitals in the metal ion. This is d7 d orbitals of CO2 plus, and in presence of field, they are increasing in energy, and in presence of tetrahedral field, they are splitting into Eg and T2g orbitals. Okay. Now the magnetic property is nothing but since there are three unpaired electrons, it is paramagnetic in nature. Okay, so this is a paramagnetic in nature. Okay, so in our next class, we will see in our next this thing, we will see how crystal field splitting of d orbitals is occurring in square planar complexes. Okay, let us end this class now, and in we will rejoin and we will start the next class, in which we will see how crystal field splitting is occurring in square planar complexes for d orbitals.